The world of atoms begins with a fascinating discovery that changed science completely. Matter is built from incredibly small particles known as atoms, according to Dalton's atomic theory. Atoms participate in chemical reactions, tirelessly transforming everything we see around us. Most importantly, atoms aren't destroyed, they follow the law of conservation of mass throughout. Delve deeper into the three fundamental particles that form the atoms: electrons, protons, and neutrons. Electrons are famously light, discovered by J.J. Thomson during his experiments with cathode rays. These tiny, negatively charged particles perform remarkable feats, traveling rapidly and ionizing gases effortlessly. Then comes the discovery of the proton by Goldstein, revealing positively charged particles in cathode rays. Chadwick's revelation of the neutron completed the trio of atomic building blocks with no charge. Did you know that the nucleus contains almost all the atom's mass despite being incredibly small? Rutherford conducted groundbreaking experiments that demonstrated most of an atom is actually empty space. Dive into the revolutionary atomic models that attempted to explain the structure of these astonishing particles. Thomson proposed a model with a positive charge spread throughout a sphere, embedding electrons within. Yet, this model couldn't solve the mystery of atomic stability and led to deeper exploration. Rutherford's daring gold foil experiment revealed a dense nucleus surrounded by orbiting electrons. The concept of quantized energy levels emerged, providing insights into atomic structure and electron behavior. Bohr further refined these ideas, suggesting electrons exist in stable orbits with defined energy levels. The wave-particle duality introduced by de Broglie challenged the classical view of atomic structure. Heisenberg's uncertainty principle flipped our understanding, illustrating the impossibility of knowing both position and momentum of particles. Schrödinger's wave equation added depth to atomic theory, interpreting electrons as wave functions instead of fixed paths. Quantum numbers were born from these concepts, describing properties of electrons with astonishing precision. The principal quantum number denotes the energy level or shell, mapping out the electron's journey. Each shell expands its domain, allowing electrons to thrive at different energy levels around the nucleus. Understanding the shapes of atomic orbitals gives us insight into how electrons are organized within the atom. Electron configurations reveal the organization of electrons, governed by principles that promote stability and order. Half-filled and completely filled orbitals showcase the unique stability they provide an atom. These concepts come together to explain everything from chemical reactions to the behavior of materials. The electromagnetic spectrum plays a crucial role in understanding how atoms interact with light. Photoelectric effect demonstrates how light can dislodge electrons, revealing energy relationships tied directly to their properties. As we explore atomic structure, we uncover the secrets of matter itself, from the smallest particles to vast collections. In this intricate dance of particles, everything comes together to form the nature of reality as we know it. The mysteries of atomic structure interweave science, philosophy, and the very essence of existence itself. Atoms, the fundamental building blocks of matter, have a rich history that began in the early 19th century. In 1803, John Dalton introduced the term atom to describe tiny, indivisible particles that form everything around us. Dalton's atomic theory laid the foundation for chemistry, stating that atoms are neither created nor destroyed during reactions. Atoms participate in chemical reactions, constantly rearranging to form new substances, showcasing their dynamic nature. Every atom consists of three primary subatomic particles: electrons, protons, and neutrons, each with unique characteristics. Electrons, discovered by J.J. Thomson in 1897, are negatively charged particles with a mass nearly 1/1837th of a proton. Protons, on the other hand, have a positive charge and a mass approximately equal to that of neutrons, establishing atomic identity. Neutrons, identified by Chadwick in 1932, are neutral particles residing in the nucleus alongside protons, adding mass without charge. Thomson's experiments with cathode rays revealed that electrons travel in straight lines, deflected by electric and magnetic fields. Goldstein's discovery of canal rays provided insight into positively charged protons, enhancing our understanding of atomic structure. Rutherford's gold foil experiment radically changed atomic theory, revealing that most of an atom's volume is just empty space. He proposed a nuclear model where a small, dense nucleus contains protons and neutrons, surrounded by orbiting electrons. Bohr's atomic model introduced quantized orbits for electrons, explaining stability and emission spectra for hydrogen atoms. The energy of an electron is quantized, changing only when it transitions between discrete energy levels or orbits. Key concepts in atomic structure include mass number, atomic number, isotopes, and isobars, defining the identity of atoms. Understanding isotopes reveals that atoms can differ in neutron numbers while retaining identical chemical properties. The electromagnetic spectrum encompasses a range of waves, each distinguished by wavelength and frequency, creating interactions in chemistry. Planck's quantum theory revolutionized physics, introducing the notion that energy is emitted in discrete packets called quanta. Light behaves both as a wave and a particle, and the photoelectric effect showcases electrons ejected from metals by photons. When light strikes metal, the energy can eject electrons, utilizing the work function and revealing essential properties of matter. Bohr's model revolutionized the understanding of atomic structure, explaining electron behavior in hydrogen-like systems through quantum mechanics. The de Broglie hypothesis asserts that particles exhibit wave-particle duality, suggesting a fundamental connection between mass and wavelength. Heisenberg's uncertainty principle challenges classical physics, asserting the impossibility of precisely knowing an electron's position and momentum. Schrödinger's wave equation describes electron behavior, providing a probabilistic view of their spatial distribution around the nucleus. The wave function determines the likelihood of finding an electron in specific orbitals, shaping our model of atomic structure. Quantum numbers uniquely describe electrons: principal, azimuthal, magnetic, and spin, providing a complete characterization of their states. Electron configurations detail how electrons fill atomic orbitals, governed by principles like Aufbau and Hund's rule to maximize stability. Exceptions to standard configurations, like those in chromium and copper, reveal the unique stability of half-filled and filled subshells. Understanding atomic orbitals guides chemistry, as shapes like S, P, D, and F significantly influence chemical bonding and reactions. Shapes of orbitals dictate the electron distribution in atoms, crucial for understanding reactivity and the formation of molecules. As students of chemistry, grasping these concepts is pivotal in unlocking the mysteries of matter and its interactions. Exploring atomic structure illuminates the intricacies of the universe, revealing how tiny particles create everything around us.